Alright, hello there. This is going to be a walkthrough for our midterm exam. So let me start my timer. So it's 7:32 right now. Alright, getting started. The true and false problem. We'll read it together and see how to solve each of these problems. First one, a system containing more than one chemical substance must be heterogeneous. So this one is false. One example is a concentrated HCl solution, like a dilute NaCl solution that's homogeneous, but it contains more than one chemical substance. All right, all ideal gas have the same density at 300 Kelvin and 1 atm. Now we have ideal gas, so that's Pb equals to nRT, and the density equals to m over v over volume. Now the mass equals to number of mole times the molecular weight. So different ideal gases will have different molecular weight. So this is false. Isobaric heat capacity Cp is an extensive property. This is true. We went over this together in class, but in short, if we think about the definition of Cp, that is dQp over dt. Or for closed system, we can write Cp equals to partial derivative of enthalpy over temperature at constant P. Now, since enthalpy is an extensive property, temperature is an intensive property, so Cp must be an extensive property. 4. For any processes in a closed system, now what we have is an expression of delta H. So we know dH equals to du plus dPv. So this is by definition true. We can do integration on both ends, or let's first write this out. So we have du plus pdv plus vdp. Now if we take the integration on both ends, then it becomes obvious, right? So this du term is for sure delta u. But these two terms are not necessarily p delta v and v delta p. So this is false. With ideal gases, Q equals to 0 for an isothermal processes, and this is false because Q equals to 0 for adiabatic processes. We went over the isothermal expansion and derived that Q is negative for an isothermal expansion, even for ideal gases in a closed system. There's a typo here. Delta S equals to 0 for any adiabatic process in a closed system. This is again false. We did this example together, so it is only true if we say it's reversible adiabatic. Because what we have in this question is that Q equals to 0. But this Q can be irreversible. Or the other way to put it is Q reversible may not equals to Q irreversible. All right, next up. Work function A is an extensive state function, while A has the same dimensionality as internal energy. So the statement is true. 1-8. Cyclic integral Q reversible must vanish for a closed system with PV work only. So this one is false. And again, when we say a cyclic integral must vanish, we're saying whatever inside the integral is a state function. So this one is false. What we can say is the cyclic integral of the Q reversible over T. And actually, I have a typo here as well. This should be dQ reversible. But nevertheless, that statement is false. Next one, a Carnot cycle must be a reversible cycle. This is just by definition true. A Carnot cycle contains 2 isothermal and 2 adiabatic, all reversible. Only two experiments are needed to decide the equation of state for any pure substance in a closed system. So this one is also true. Remember, we have 6 partial derivatives. And then we reduced it to 2 partial derivatives for P, T, and B. And since we are stating we have a pure substance in a closed system, so no chemical reaction and no material exchange. All right, so that's all of our true and false. We are at 7:38 now. Next up, short answer problems. So this part is just, well, reading the question and give a quick answer. Let's get started here. Given the osmotic pressure, big delta equals to CBRT. The unit of big delta is the same as pressure. Right? So what we have on the left-hand side, we have pressure, or we can write its SI unit as Pascal. And on the right-hand side, we have a question mark times RT. So R is joule per mole per Kelvin, and temperature as a unit of Kelvin. So my Kelvin cancels out. My Pascal is the same as Newton per meter square, and my joule is Newton meter. All right, so in order to get the unit on the left-hand side, the unit of my CB must be, well, Newton cancel out, so that's mole per meter cube. All right. And think about, is my CB an extensive or intensive property? What exactly is my CB? So in here, on top, we have an extensive. On the bottom, we also have an extensive. So this is an intensive property. And thinking about what is the nature of my CB, that's my concentration. All right, next one, derivation. This is exactly the same derivation we did in class. What we are doing here, different ways to approach it, but we can just write out the definition of Cp and mu Gt in closed system equilibrium PV work. We got the Cp equals to dH over dt at constant P, mu Jt, the Joule-Thomson coefficient, equals to dt over dP at constant H. And let's write it out. What do we have here? We have straight partial derivatives with respect to T, H, and P. So we can use our cyclic rule. So dH, wait, is it classical? Over dt at constant P, dt over dP at constant H, dP over dH at constant T. That's equals to -1. So in here, that's my Cp. dt over dP at constant H, that's my mu Jt. I want to move this term to the right and flip it. So that's on the right, we have partial derivative of H over P at constant T. So we're happy. All right, next up. This one is a little bit challenging because it requires you to use 2 different types of knowledge. So the first type is qualitative. Say we have a cold reservoir at 0 degree and a hot reservoir at 5,000 degrees Celsius. So let me just translate that into Kelvin. What it asks is what's the maximum efficiency that can be obtained for a heat pump? So in this question, effectively what we are saying is what is the maximum efficiency? So remember our Carnot's principle. A reversible cycle as the most efficient one. So, what do we have? We have our Carnot cycle as a reversible cycle. We can use the efficiency of my Carnot cycle. That's 1 minus Tc over Th equals to 1 minus T73 by T. That gives you 0.948. Next question, what is the maximum efficiency if we run the heat pump backwards? So now imagine we're running the heat pump backwards. And then what do we have? Well, a reversible cycle will be able to run it both forward and backward, so the efficiency will be the same. All right, next one. For an ideal gas with CPm, or the molar isobaric heat capacity, equals to AT plus BT squared, what is A and B? In which A and B are constants. The question is, what is CV? So what do we know? We know that CV equals to Cp minus Nr, and then Cp equals to N times Cpm. So we can write our CV expression as ANT plus BNT cube minus Nr. Second part, write an expression of delta U when N more of this ideal gas goes from T1 to T2. Right, so what do we have? We have du equals to Cv dt for ideal gases. My delta U dot equals to the integral of the Cv that we just write out from T1 to T2. We have ANT plus BNT cube minus Nr dt. So that's effectively solving this integral as a math problem. So we have 1/2 ANT T final squared plus 1/4 Bn T to the fourth minus Nr T2 minus our initial temperature ANT1 squared plus 1/4 BNT1/4 minus nRT1. All right, next up. Calculate delta S for the mixing of 10 grams of helium with 20 grams of argon at 100 degrees Celsius and 1 atm, assuming all gases are ideal. And it's given our molecular weight. So we're mixing of ideal gases. Right, so we can use the delta S we derived to be equal to negative NaR ln chi A minus NaR ln chi B. Right, Na is number of mole and chi is the mole concentration. What do we have? Number of mole of Na, that's 2.5 mole times 8.314 ln 5/6 minus 0.5 times 8.314 ln 1/6, and that's in joule per Kelvin. The more cancels out. Plugging in our calculator, we get that equals to 11.2 joule per Kelvin. All right. Okay, now we're at 747. Moving on to our comprehensive problem. Let's read it together first. We have a perfect gas undergoes a reversible isobaric compression process in a closed system. So a few things we know, right? So perfect gas, we have PV equals to nRT. We have du equals to Cv dt, dH equals to Cp dt. For this question, it undergoes a reversible isobaric compression. So reversible tells us we have ds equals to TdS. ds equals to TdQ. Isobaric says it's constant pressure, so we have Qp equals to delta H. Compression tells me my V final is smaller than my V initial. So there are several things we know by just reading this problem. First of all, we have Qp equals to delta H. Now in the question, it's asking us to calculate the heat and delta H, so we can use this as a sanity check to double check our calculation is correct. In addition, we have definition of enthalpy, which equals to U plus PV. So we can also calculate internal energy in different way, either using CVDT or using the definition of enthalpy. Oh yeah, and I forgot to say reversible. We have W reversible equals to negative PdV. Okay, so now we're ready to get started. For each of the following processes, if possible, write an expression of the following quantities using V initial, V final, number of mole, R, and P. Circle whether each quantity is positive, negative, zero, or not enough information. And we're giving you the hint saying you don't need to solve the question in the given order. Because again, we have different ways to solve this problem. Let's get started. Expression of work. Now work is quite straightforward. For a reversible processes, we have dW reversible equals to negative PdV. Or taking integral on both ends, we got work reversible equals to integral of negative PdV from V initial to V final. And that's just negative pressure times V final minus V initial. Now this is a compression, so my V final minus V initial is negative. And here we have a negative sign in the front, so my work is positive. Right. And then Q. Q, we have two different ways to solve it. Let's say we can start by doing it using QP equals to delta H, thus equals to the integral of Cp dt. Now, do we know what Cp is? We know what Cv is, and we know that for ideal gases, Cp equals to Cv plus Nr, so my Cp equals to 7/2 times Nr. T final minus T initial. Now we want our expression in V final, V initial, Nr, and P. So we translate that T final minus T initial using PV equals to nRT. Right, so that becomes 7/2 Nr times PV final over Nr minus PV initial over Nr. So my Nr cancel out, my pressure is constant. My Qp equals to 7/2 times P V final minus V initial. And since V final minus V initial is negative, my Q must be negative. And also in here, we have already solved my delta H. We can solve my QP using a different way. We can solve it by using the first law of thermodynamics, which is Q equals to delta U minus W. We know what W is. Let's just write out an expression for delta U. Now, similar to what we had before, my delta U equals to T1, T2 CV dt. Right, we know what CV is. That's the 5 over 2 NR. That's the 5 over 2 NR times T2 minus T1. And then likewise, we translate our temperature into pressure. So we have PV final over NR minus PV initial over NR. And we got our delta U equals to 5 over 2 NR cancel out. And my P comes out. We have V final minus V initial. And again, my V final minus V initial is negative. So my delta U is negative. Now going back and try to solve my Q equals to delta U minus W. So my delta U equals to 5 over 2 P V final minus V initial minus my work, which is negative P V final minus V initial. Remember this negative sign here in front of my work reversible. And we end up getting 7 over 2 P times V final minus V initial, and we are happy. Next up, expression of delta H. So we can solve delta H by using QP equals to delta H, and that's the same as we solved before, 7 over 2 P times V final minus V initial. Or we can also solve delta H using the H equals to U plus PV, or for constant pressure, what we have is delta H equals to delta U plus P delta V. Right, so delta U, that's 5 over 2 P V final minus V initial plus P times delta V, which is V final minus V initial. And likewise, we get the same result of 7 over 2 P V final minus V initial. And this must be a negative number since my V final minus V initial is negative. And these two numbers checked out. We're happy. All right, next up, delta S. So this is the change of state. What we have reversible change of state. So for delta S, reversible change of state, we can use the equation we derived, which is from T1 to T2, CV over T dt plus NR log V final over V initial. Solve this integral. The first integral, we have CV times log T final over T initial plus NR log V final over V initial. Now what is my T final over T initial? We have T final over T initial, that equals to, well, PV final over NR divided by PV initial over NR. So these terms cancel out. They're all constant. We have T final over T initial effectively equal to V final over V initial. And we can write this out as 5 over 2 NR log V final over V initial plus NR log V final over V initial. We get our final result as 7 over 2 NR log V final over V initial. Now in this case, thinking about this number here, our final is smaller than initial, so this logarithm is a negative number. And my delta S is thus a negative number. All right, so we are at 757 now. All right, that's a walkthrough for our midterm exam. We'll hopefully post your grade by Wednesday.